intended learning objectives. First, you will be able to calculate the writing arm at large heel angles. Next, calculate for the angle of Loll. Before we can proceed with the intended learning objectives that we have this prerequisite knowledge. So understanding hydrostatic table. Now, hydrostatic table is within the ship's stability booklet and contains the following informations: the vertical, longitudinal, and transverse center of gravity, vertical, longitudinal, and transverse center of buoyancy, mass displacement of the ship, volume displacement of the ship, longitudinal transverse center of flotation, metacenter, metacentric height, metacentric radius or BM, moment of change stream by 1 cm or MCTC, tons per centimeter immersion or TPC. So we have this example. This is the hydrostatic table, but this is not the complete one with complete details, but at least we have here a picture. So as you can see here, we have the mean graph and we have the equivalent values for the displacement in tons and the displacement in volume, and we have also the tons per centimeter or tons per immersion 1 centimeter TPC, then LCB, LCF, MTC, and so on. So which means that the value will change depending on the change of the mean drop of the vessel. So all we need to determine is the mean drop of the vessel, and we already have these values because these values are already calculated by the naval architects. That's why we just need to understand how we will be able to use them in our job. So we have here the writing arm or lever. This is the distance between the forces of buoyancy and gravity and is known as GZ. So in this illustration, we have here the vessel heeling on one side, and we have here the center of buoyancy acting downward and the center of buoyancy in line with the metacenter acting upward, in which it will going to make our ship upright again. That's why it is called writing arm or lever. So to give you a wider understanding of GZ, let's have the ship's nomenclature. So we have the base of the keel and the metacenter. By the way, the metacenter will change depending on the vessel's mean draft. So again, it will change depending on the vessel's mean draft. Then we have the center of the gravity. Then we have the center of buoyancy. In this case, we have an upright vessel with a positive GM. So what will happen if the ship will tilt to one side? or heel to one side. So obviously, the center of buoyancy will move towards the lower side and will be in line with the meta center. So there will be a force acting downward and a force acting upward to make the ship upright again. So we have there the writing arm, which is the GZ. Writing moment is another story, so I will not discuss this one as of this moment. So let's just skip that. Now, what will happen if we have a negative GM? If the ship will incline to one side, having a negative GM, again, the center of buoyancy moves to the lower side and will be in line with the force acting upward with the metacenter, but it will be already a capsizing arm because we have a negative GM. So instead of helping the ship to become upright, it will add on to the moment where the ship will be tilted more. Okay? So if we have a negative GM, then we will have also a negative GZ. And it is not known already as writing arm, but instead capsizing arm. Now if we have a ship which is or which has a 0 GM or a neutral stability, if it will tilt to one side, then the line of force will be equal. So it means that there is no writing arm. And if it will shift or it will tilt to one side, it will not have the moment or it will not have the capacity to return to its upright position anymore. Okay, we have a 0 GZ and 0 GM. So we have the relationship between GM and GZ. If GM is positive, then we have a positive GZ. But if we have a 0 GM, then we will also have a 0 GZ. If we will have a negative GM, then we will also have a negative GZ. So which means that the relationship between GM and GZ is proportional to each other. Okay, so what is the formula for GZ at small angles of inclination? So you have this one in your basic stability and trim the past semester. I have GZ equals GM times sine of angle kill. Now take note that small angles of inclination is up to 15 degrees only, and more than that is considered as large angle of inclination, and we have another formula for that, which is GZ equals GM plus open parenthesis 1/2 BM times tangent squared of the uh, heel, then times sine um, degrees of heel. So we have here a sample problem. In order for us to achieve the intended learning objective, to calculate GZ at large angle of inclination. So we have a vessel of 3,000 tons displacement has a GM of 0.5 meter and a KB of 1.81 meter and KG of 6 meters. It is floating at 4 meters mean draft. This is the mean draft, and upon looking at our stability booklet, we have there the equivalent displacement, and we have there KB, and then we have there KG and KM. So how did we have GM here? So I suppose that it is already calculated that KG minus KM equals GM. So it means that if we are going to add GM to KG, then that would be our KM. So we have here a positive stability where G is below the metacenter. The center of gravity is below the metacenter. Okay, so we need to calculate first for the BM. Okay, for the BM. So we have a given KG and a given GM. The question is, how much is the BM? So of course, we must first obtain the value of KM. So how are we going to do that? We should first add KG to GM in order for us to determine the value of KM. Okay? And right after that, we are going to subtract it to the value of KB so that we will be able to get the value of BM. Okay? So again, we have GM plus KG in order for us to obtain the value of KM. Then after obtaining the value of KM, which is 6.5, it will be subtracted to the value of KB. Then that will be the BM or the metacentric radius. Now since we have 25 degrees as the angle of heel, so we could not use the small angle of heel formula, but instead the large angle. Okay, so just use the given values. So 0.5 plus open parenthesis 1/2 metacentric radius times tangent 25 degrees squared times sine 25 degrees. Then we have here um, 0.5 plus open parenthesis, the result would be 2.34375. Then we have times 0.2174 times 0.4226. Just use the correct mathematical equation and you will be able to derive from the result of 0.43 meter for the GZ. Now let's move on to the next intended learning objective. I hope that the previous topic or the previous slides will help us to understand the formula for the angle of Loll. Now we have here the tangent angle of Loll equals square root 2 times GM divided by BM. So in this case, since we have already our main graph, then we only need to obtain the value of GM and BM. Okay? So our example, as I said, we have the given displacement because um, we have already the draft, no, at 2 meters. So it means that we are going to achieve the value of Kg, Kb, and Km at our hydrostatic table, and here is it already. Then we could calculate for the angle of Loll. Okay, so why is it that it becomes the angle of Loll? Because it is a negative GM. Because the angle of Loll is caused by a negative GM. So this is the picture of the example. So we have here a negative GM where Kg, the height of the center of gravity above the base of the keel, is larger or greater than the Km, which is the height of the meta center above the base of the keel. Therefore, we have an unstable ship. Okay, so we have the solution for this one. So first, we need to obtain the value of GM and BM in order for us to apply it in our formula. So we have the given Km and Kg. So simply subtract the two and we have there the negative GM. Now again, this is normal since we are looking for the angle of Loll which is caused by negative GM. So I'm sorry for the wrong spelling. Now we have BM which is equal to Km minus Kb. Okay, so we have the given values 2.5 meters minus 1. BM is equal to 1.5 meters. So we have GM negative 0.5 meters and BM which is 1.5 meters. So just use the formula tangent angle of Loll equals square root of 2 times GM divided by BM. So just use the given for the answer for GM and BM, 2 times GM which is 0.5 divided by 1.5. Okay, so just ignore the negative sign here. Okay, do not use that one. So just input 0.5 divided by 1.5, so that is equivalent to 0.816. Then the angle of Loll equals ship tangent 0.816, then the angle of Loll is 39 degrees 14 minutes. It means that if the ship will um, incline, no, to an angle of 39 degrees 14 minutes, it will have the negative GM, or since GM is proportional to GZ, then we will have also a capsizing arm. Now, what is the importance of knowing the formula for GZ at small angle of inclination up to 15 degrees, and above that, that is for large angle of inclination, and also for the angle of Loll? That is because it is very vital in understanding the GZ orb. Okay, so without understanding the formula, you will not be able to understand what is within the curves, no? So you have there the GZ, no, at this side, and you have here at the bottom part, you have the angle of heel. Okay, so that is the angle of heel. So how did the naval architect provide this one? By simply computing the GZ up to small angle and applying the large angle up to here, and on this portion here we have the 0 GZ, and that is already the angle of Loll. Again, therefore, we need to mention formulas above to make a GZ curve. So that's it. I hope that we have achieved the intended learning objectives to calculate GZ at large angle of inclination, and also to give the formula for the angle of